let's do a more practical example. Something that is pretty popular here in Utah is to go mountain climbing, and your ropes are sold with a force constant, or at least with a force rating, I should say. So you've got a rope hanging here, and you have a climber who's using the rope, right? And this rope has a rating of 1.40 times 10 to the 4 newtons per meter. So that's basically telling you how stretchy the rope is. And let's say this climber is 90 kilograms. So the question is, for fun, what's the oscillation frequency if you just bounced on this rope? If you displaced yourself, what would the frequency be? But more importantly is that if you suddenly fell, how far would the rope stretch before you came to a stop? So we're going to do those two problems. So the first thing we're going to do is look at the frequency. So write down here that the angular frequency is equal to 2 pi times f, and that's equal to the square root of the ratio k over m. So that means my frequency is 1 over 2 pi times the square root of k over m. And I actually know all these things, so I'm just going to go and put that in there, and I get 1 over 2 pi times the square root of 1.4 times 10 to the 4 divided by 90. And I actually used my calculator this time, and I wind up with 1.99 hertz, or about 2 hertz. In other words, your frequency is going to be a couple of times per second. So that gives you an idea of, imagine bouncing on this rope if you dropped. But more importantly, what is the stretch? So imagine this climber falls 2 meters. Okay, that's probably about as far as you want to fall. So fall 2 meters, we're going to treat that as the height. And the question is, what happens to the stretch of this rope when that occurs? Well, what's going to happen is that the energy that you had stored in your potential energy is going to be transferred to the rope, and that's going to cause the rope to stretch. So we have our initial energy, so we're going to do this as an energy problem. We have our initial energy is equal to mgh. And we have our final energy is going to be stored in the spring, and that is going to be the potential energy of the spring is 1/2 kx squared, as you learned in your chapter. So we're going to set these things equal to each other. So we go from potential energy in the gravity to potential energy in the spring. I don't worry about how fast you're falling, and I just get mgh is equal to 1/2 kx squared. And what we want to know is what happens to x. So that's going to give me the square root of 2mgh over k. And if I work that out, that's going to give me about 1/2 meter, which is a lot. Okay, so maybe we want to double up this rope. So the question is, what happens if we double up this rope? And that's the same thing as effectively as making the spring constant twice as strong. Now, rather than do this whole calculation again, I'm just going to look at this k and notice that it scales like the square root, inversely proportional to the square root of k. So I can just do a ratio. I can say, well, what if k goes to 2k? And I can say, well, my initial displacement was x. I'm going to have my final displacement xf. That's just going to be the square root of 2mgh over k divided by the square root of 2mgh over 2k. And you'll notice that all of that is going to cancel except for the 1 over square root of 2 down here, which is equal to the square root of 2 there. That means my xf is equal to my original x divided by root 2, which is 0.5 divided by root 2, which is a significantly less amount. So my significance here is that, as expected, xf is smaller. And a good reason to double up your rope.